Why can a AA and AAA battery both produce 1.5 volts when one is almost twice the size? Why is a huge D battery still only 1.5 volts? Why is a tiny coin cell able to run a device for years? And what is actually hiding inside that rectangular 9-volt battery? The answer is that battery size is not just about voltage. Different batteries are built for different amounts of energy, current, runtime, space, and devices. The AAA battery. The AAA is one of the smallest cylindrical batteries you will find around the house. A standard alkaline AAA produces about 1.5 volts, exactly the same nominal voltage as a much larger AA, C, or D alkaline battery. So why make it smaller? Because many devices do not need much energy. A television remote, wireless mouse, small flashlight, digital thermometer, or other compact electronic device may only draw a small amount of current. Putting a large D battery inside would give much more runtime, but it would also make the device enormous. The AAA solves that problem. It provides the required voltage in a much smaller package. But that smaller size means there is less active material inside, so there is less stored energy available. That is why AAA batteries usually do not last as long as AA batteries when both are powering a similar load. They are also less suited to devices that demand large bursts of current. This is the first important battery rule. Voltage tells you how strongly the battery can push electrical charge. It does not tell you how long that battery can keep doing it. The AA battery. The AA is probably the most common battery size in the world. Like the AAA, a standard alkaline AA produces around 1.5 volts. Again, the extra size is not there to create more voltage. It's there mainly to store more energy and support devices that may need longer runtime or greater current. AA batteries appear in everything from toys and game controllers to flashlights, clocks, wireless equipment, cameras, and portable electronics. And here's where something interesting happens. Put two AA batteries in series and their voltage adds together. Two 1.5-volt batteries give approximately 3 volts. 4 give approximately 6 volts. But place batteries in a different electrical arrangement and you can increase available capacity while keeping the voltage similar. So when a device uses 4 batteries, it is not automatically doing that simply because one battery is too weak. The designer is choosing a combination of voltage, runtime, available current, cost, and physical size. AA batteries also come in different chemistries. A normal disposable alkaline AA is around 1.5 volts. A rechargeable nickel metal hydride AA is normally around 1.2 volts. They fit in the same battery compartment, but internally they are completely different systems. That is why physical size alone does not tell you everything about a battery. The C battery. Now we get to the battery that looks like someone took a AA and scaled it up. A standard alkaline C cell is still around 1.5 volts. Again, the extra size is not there to create more voltage. It's there mainly to store more energy and support devices that may need longer runtime or greater current. C batteries have traditionally been used in larger flashlights, portable radios, toys, musical equipment, and other devices that need more power than a small AA is comfortable supplying for long periods. Think of voltage like water pressure and battery capacity like the amount of water available in the tank. A AA and a C battery can provide similar electrical pressure, but the C battery has a much larger tank. That larger body also allows it to handle sustained loads better than smaller cells of similar chemistry. So could you technically power some C battery devices using AA batteries if the voltage matched? In certain situations, yes, but they would usually run for much less time, and high current equipment may perform poorly. The device was designed around more than just the number printed in volts. The D battery. The D battery takes the same idea even further. It's large, heavy, and once again, a standard alkaline D battery produces only around 1.5 volts. Again, the extra size is not there to create more voltage. It's there mainly to store more energy and support devices that may need longer runtime or greater current. Large flashlights, emergency lanterns, portable equipment, older radios, motorized toys, and other high-drain or long runtime devices have commonly used D cells for exactly this reason. Imagine placing a AAA battery next to a D battery. Both may say 1.5 volts. Slightly amused, but asking why the D battery is bigger is like asking why a motorcycle and a truck can both travel at 60 miles per hour. Speed is only one measurement. The same principle applies here. Voltage is only one part of battery performance. Capacity, internal resistance, current capability, and runtime matter too. And because a D cell can contain several times more usable energy than a small AAA, it can keep the same type of device running much longer.
The 9-volt battery. Now things get strange. The 9-volt battery is rectangular. It has both terminals on the top, and instead of producing the familiar 1.5 volts, it produces around 9 volts. So how does one little rectangular battery suddenly create 6 times the voltage of a AA? Because inside a common alkaline 9-volt battery, you are not really dealing with one 1.5-volt cell. You have multiple small cells connected together in series. In a typical alkaline design, 6 individual cells combine to produce approximately 9 volts. The rectangular outer case is basically packaging that keeps those cells together and gives you 2 convenient terminals on top. That also explains why a 9-volt battery is not simply a more powerful AA. Its higher voltage is useful for devices designed around that electrical system, such as smoke alarms, test equipment, small electronic circuits, wireless microphones, and certain sensors. But its compact internal cells mean capacity is not necessarily enormous. A large D battery may store significantly more total energy, even though its voltage is much lower. And there is one practical detail worth remembering. The positive and negative terminals of a 9-volt battery sit extremely close together. A loose metal object can bridge both terminals and create a short circuit. That is why storing loose 9-volt batteries beside keys, screws, or other metal objects is a bad idea. The coin cell. The coin cell is one of the most impressive examples of designing a battery around the device instead of designing the device around the battery. These cells are wide, flat, and extremely thin. A common example is the CR2032 lithium coin cell used in computer motherboards, car key fobs, digital scales, small remotes, calculators, sensors, and other low-power electronics. A CR2032 typically produces around 3 volts. That tiny battery can sometimes operate a device for months or even years. But there is no magic happening. The secret is that the device may be using an incredibly small amount of current. A motherboard clock circuit does not need the same electrical power as a flashlight motor. If the load is tiny enough, even a small amount of stored energy can last an extremely long time. Coin cells are therefore excellent for compact electronics that need low current and long shelf life. They are not designed to replace a AA in a high-drain device. Try asking a tiny coin cell to continuously power a large motor, and its limitations become obvious very quickly. And there is an important safety issue with these batteries. Their small, shiny shape makes them especially dangerous if swallowed, particularly for children. A swallowed coin or button battery can cause severe internal injury and needs immediate emergency attention. The button cell. Button cells are easy to confuse with coin cells because both are small round batteries. But button cells are generally smaller and thicker relative to their diameter, more like a tiny button than a flat coin. You'll find them in watches, calculators, small medical devices, laser pointers, measuring instruments, hearing-related electronics, and other extremely compact products. Different chemistries exist. Some alkaline button cells produce around 1.5 volts. Silver oxide versions are also commonly around 1.55 volts and are valued for maintaining a relatively stable voltage during use. Different button cells may look almost identical while having different dimensions, chemistry, capacity, and electrical characteristics. That means replacing one based only on it looks about the same size is not a good strategy. The code printed on the cell matters. Even a tiny difference in thickness can prevent the battery cover from closing or stop the electrical contacts from touching correctly. And just like coin cells, these batteries are intended mainly for low-power devices. Their strength is compact size and long service under small loads, not delivering huge amounts of current. And now the difference between all these batteries becomes much clearer. The AAA gives low-power devices 1.5 volts in a compact package. The AA keeps the same basic voltage but offers more capacity and current capability. The C cell increases that energy storage further for larger equipment. The D cell provides much greater runtime and sustained current while still remaining around 1.5 volts in its common alkaline form. The 9-volt battery combines multiple internal cells to create a much higher voltage in one convenient package. The coin cell sacrifices current capability for an extremely thin shape, long shelf life, and tiny device compatibility. The button cell becomes even smaller for watches and miniature electronics. And the rechargeable 18650 lithium-ion cell uses lithium-ion chemistry to provide much higher voltage, rechargeable operation, and significant energy in a cylindrical package. So when you see a shelf full of batteries, don't ask only which one is bigger. Ask what the device actually needs: voltage, capacity, current, runtime, physical size, chemistry, and whether the battery is designed to be recharged. Because a AA, D cell, coin cell, and 18650 may all be called batteries, but inside the device they're solving completely different problems. And that's exactly why they look so different. Which of these battery types do you actually use the most, and is there one you never understood until now? Tell me in the comments. And if this helped you finally understand what all these different batteries are actually for, subscribe. There's a lot more of this coming.